All right, so I think this is going to be a little quicker. So I think I'll do a quick kind of run through. So the basic idea is to use big data to be able to figure out what are the markers that will predict your biological age versus your chronological age. And if you think about a kind of simplified model, what aging is your chance of dying in any given year increases as you get older and older and older, right? And so there's a standard curve that says what's the mortality in a year for your given chronological age, and that's sort of the average across the population. But within that population, there's a spread that you could think of as your biological age, where if your probability is lower than a person normal for your age, then your biological age may be younger. If your probability is higher, your biological age may be higher. And so in some sense, you could project that onto this graph and figure out what your actual biological age is. And it'd be interesting to understand what are the factors that actually affect that. So the idea is that we could use the data that we are gathering already on people, which may include their medical record data, might include genomics, it might include fitness data, lifestyle data, all sorts of things. And from there, be able to predict, okay, this factor increases your biological age by whatever, 2 days, and this decreases it by a month, and you add up all of those factors, or you run the machine learning model, and it says, all right, this is your effective biological age predicted based upon what we know about you. And then, the longer term thing of this is you go back and you look at what are the factors that most affect your biological age, and then you can think about what are interventions that can increase those. So you can go back and say, oh yeah, exercising or sleep or not eating this or taking these supplements or having this condition. Those are things that you might want to change. And so this is actually a fairly straightforward big data problem. The hard part is actually getting access to the training data because it is very personal health information, and so you need to go through an IRB approval or a data access committee, and you have to treat this data fairly carefully and make sure that you don't expose any individual personal data when it comes out. But there are sources of this data. There's the UK Biobank that has 500,000 people with full electronic medical records from the NHS, plus they're genotyped with genotype chips, the equivalent of 23andMe data, and then they have various other lab tests and so on that might be available on these people. And there are others. There's coming up, it's called All of Us, or the Precision Medicine Initiative in the US. If you work within a given institution like Stanford, you can get access to the medical records within there. And so the idea is we just take this huge training data, we'd simply do a time series analysis where we say, okay, at a given year, look back 5 years at all of those people. You look forward and see which of those died or didn't die in the subsequent year, and build a model that's the best thing that you can do to predict that. And there's a huge array of machine learning models that you might be able to use. Variational autoencoders, sort of dimensionality reduction things like struct-dvec and word-dvec. You want explainable models, so maybe use a generalized additive model instead of a neural network. There's tons of technology to do that. You build, and then you can build a model. So this is actually a relatively simple, small-scale project. The main steps are you just need to basically, in some sense, a big part of the work is just acquiring access to the data, writing the research proposal, going through the IRB and getting access to it. And then the usual sort of data wrangling and feature extraction and experimenting with a bunch of different learning models until you figure out something that works. And then, the interesting thing, once you've done, having the predictor is great. That's sort of a useful thing. And then the interesting thing is now going back and sort of reverse engineering your model and being able to figure out what are the causative factors. And then that can spur a bunch of interesting research into what you might want to change, or how these things, if you find something surprising, how does that actually affect your health? It shouldn't be a big project. It's probably 3 to 6 months of work. A few people, maybe even one person to do the real work, and a couple of PIs to supervise or whatever. And you end up with a publication, you end up with a model, maybe some software. And then I think the long-term impact is really, this reverse engineering of the model, so you can actually identify what are these key biomarkers, and then figure out, what you want to do in an actionable sense to be able to actually lower your biological age. That's it. Questions?
Thank you, Ravi. Okay, so we have a couple minutes for questions. We'll first take any questions from our judges.
Have you chosen the marker? Do you have any idea what the markers would be? Because there's a lot of controversy over what markers.
The point is you don't choose in advance. You just throw in as much data as you can, and you just figure out what's predictive. Now, you want this to be be able to reverse engineer the models, because you might find out things that are, not necessarily useful. Like, okay, the fact that someone had a heart attack that's a negative indicator for their mortality, but that's not necessarily.
But you have to make a decision on chronological versus biological age, right?
Yeah.
So how do you make that decision?
So what we do is you say, all right, what is predictive of you being likely, any given person being likely to die in the subsequent year from which so you pick a date, January 1st, 1985. You look backwards 5 years and forward 1 year. Very simple.
Okay, but how about this? What types of data are you looking for? Are you looking at genomic data, genomic data?
And I think the interesting thing would be if you can get electronic health records. And so that has a lot of phenotype data, it has lab tests, there's a lot of interesting biases and complexity in dealing with that data, but it's also a very rich data source.